Great. So let's go ahead and get started. So, kind of some disclaimers stuff, should be used as a guide, is not all-encompassing. We're not representing AP, all that good stuff. You guys know we're volunteer and not representative of the College Board at all. So let's start off with what we're going to take a look at today. So, big idea three, which is called algorithms in programming, is very big in the course. It's almost a third, if not a third, of your exam. So that's kind of why I chose this specific unit. Don't have a lot of time this semester, so unfortunately, I can't do a lot of lectures, but I thought this one would be a good one to do. Okay, so here are all of the subproblems, subtopics, I should say, that are in Unit 3. We'll talk about what a subproblem is later, but so we're gonna try and hit every single one of them. Some of them are longer than others, but yeah, so let's jump right in if there's no questions. Yeah, so here's kind of the formats of how we're gonna do each of these. So what is the topic? And then how can I be tested on this topic? And then some practice multiple choice. So let's get to work. All right, so variables and assignments. So the first question, and I kind of formatted this as more of a question and answer type of vibe. But the first question is, what is a variable? So can somebody kind of tell me what a variable is, maybe? So like I mentioned, I love participation. So very, very simplistic, I know. Some of these questions will be very straightforward, but I think it's good to kind of get us talking. And then we can kind of do some discussions and stuff, you know? Um, X. Yeah, perfect. There you go. X works perfectly, right? X is an example of something that could be a variable, right? A component of the program that can vary and change with inputs and container for value. Absolutely. All these are right. Perfect answers. I love actually what Yoster, I don't know, what you said about being like a box. That's how I visualize it a lot, is kind of putting values into a box or like a packing, like a some sort of container, right? Absolutely. Okay, so I guess from the CED, right? No, sorry, Haley, this is not psych. This is computer science. So you're welcome to stay, but if you're looking for psych, that's not here. Yep. So a variable, you can kind of think as we can kind of say it's like an abstraction, or sorry, it's like a data storage, right? Which is kind of what we said. Now, is it possible, by the way, that a variable can store multiple things, or is it just one? Yes, it is, right? It's in a list. Absolutely. Yeah, absolutely. Okay, good to know. Good to know. So, what are some kind of common things that we may want to think about when we're naming a variable? Yeah, so what it's being used for, right? Its purpose. Yeah, exactly. And we want to be clean with it. We don't want to be naming everything X, A, B, right? Because then we won't know what we're doing, right? Something that directly relates to the value. Absolutely, right. So meaningful names really help with the readability, we agree. So we'll say meaningful names help with readability. All right. What is a data type? Here's a good question, right? So, in different programming languages, some some languages say that everything is the same, right? Whereas others kind of distinctly tell you what types of data that you could be storing in a variable, right? So great, a string is a great example of like a data type that you could be thinking of, right? The kind of information you're holding. That's exactly what I'm gonna write right here. I'm just gonna do this, copy paste. There you go. The kind of information you're holding. Um, that's exactly right. Um, 1 plus 2 equals 3, or 1 plus 2 equals 12. Well, when we're thinking about data types, we can kind of think of them more as like integers, right? Instead of thinking maybe like how something equals something, we can say what exactly they are, right? They're integers. And so great. So on the test then, how are we going to be tested on uh Ah, yes, I see what you're saying. Yes. So 1 plus 2 you could consider as integers, which then their answer to their addition would be 3. But if we were to concatenate them and say that they're strings and concatenate them, then we would say 1 plus 2 is actually 1, 2, right? Not 12 per se. So thank you for clarifying because I was reading it wrong. Okay, so as far as on the test, we should expect questions that ask us to identify what results are stored in the variables after some operations are done with it. And so how we can kind of identify those questions are, well, let's take a look. So, for example, let's consider this one. CSP has to be the exam with the worst curve known to mankind. Yes, I agree. It's tough, but I believe we can do it. Yes, I can zoom in. Thank you for asking that. Great. So consider the following code segment, which uses the variables r, s, and t. So we want to figure out what is displayed as a result of running this code segment. So I'm going to leave you guys like a minute or so here. And this is probably how we'll do these is take a look, see if you can answer it on your own, and then we'll come back together and explain and see what we got. So you can put your answer in a spoiler. If you don't know how to do a spoiler, you can write your answer and then highlight it and click the spoiler. Or I think there's a hotkey. It's like if you put two double bars, or you put two bars and then write your answer and then close it with two more bars, you'll get uh, you'll get a spoiler. Yeah, so Leaf, that's exactly how you're going to do the spoiler. But you can put your answer in there as well. So if you do, let me see here. I'm gonna tell you how to do it right now. So if you type this into Discord and then replace answer with what you want to put, that's how you're going to do a spoiler. Yeah, so it seems like we're all getting the right answer. So that's great. So the answer is going to be B here. So let's go over why that is. So the idea with these types of questions is pretty much just output tracing, right? Or in other words, what does the program result in, right? And that's going to be a large majority, or not maybe not a majority, but that's going to be a large percentage of what the types of questions from this unit are going to look like, right? It's going to be tracing the output from a given code. So let's take a look. R gets 4. So what that means is 4, we can kind of think of R as a box that 4 is being stored in. And now when S gets 5, it's the same exact thing, right? T now is going to get the result of multiplying R and S. So if we do that, 4 times 5 is going to be 20, right? So 20 is going to be going into the box labeled T. So we have 4, 5, and 20. Oh, I don't know why that happened. Give me 1 second. Thank you. Yep, I got you. Thank you so much for let me know. That's so weird. I don't know why that happened. Maybe my internet or something. Okay, you guys got it? Yes, perfect. Okay, cool. So R times S is 20, and that's gonna be stored in the T box, right? So now we're going into the S box, which we already know is 5, but we're going to replace it with the result of what's currently there in S minus R. So S minus R, that's 5 minus 4. So the new value of S is actually going to be 1. So this is kind of like a tricky part for some kind of newbies at coding is replacing a value that's already in there using the value itself. So if we have S, we said that's now going to be 1 because it was 5 minus 4, which is 1. So R now is going to get T over R. So T we said was 20, and R we said is 4. So 20 divided by 4 is 5. We know. So 5 is going to be what's put in the box R. So then we know that 5 minus the 1 is going to be 4. So that's why we get 4. So there's a lot of questions like these on the test. I wouldn't be surprised if you saw at least one of them. Cool. Any questions with how we did this one before we move on to the next kind of subtopic? All right, let's do it. So the questions are going to wrap up in difficulty pretty quickly here. This one's a little bit more tricky. So, but first, let's answer some questions about some data abstraction. So, what is data abstraction? That's probably the question, right? So, when I'm thinking of data abstraction, I always think of one thing that I memorize, and so I will impart some advice onto you as we uh, kind of discover what data abstraction is. But what do you guys think the concept of data abstraction actually means? Yeah, so making complex things simpler by grouping it together, taking the data from big set to data, big set of data to use. It simplifies the code, simplify it. Perfect, right? So the idea is with abstraction, we can take, um, we can kind of use a, what we have in our code, but group things together that are similar in order to kind of make it less complicated, right? And so it kind of provides this sort of separation between the abstract properties of a data type and the concrete details, right? So what we'll say is it groups similar things together to create a bigger picture um, view, we'll say. Kind of abstract answer, right? But that's what this is, right? Where it's a more, abstract concept. That's it's abstraction after all, right? So, let's see, what is a list and how are they used? So we kind of touched on this a little bit, right? But a list just stores multiple um, items in one variable. So now the question is, what's the difference between an index and an element? So what do you guys think the difference is? Is it out again? This is so weird. I wonder why it's happening. Thank you for telling me. Let's try sharing the window instead this time. See if that helps. All right, so what we're looking at now is the difference between an index and an element. Index is the location where an element is at, usually starts at 0. An element is the actual data stored in a location. That's absolutely right. So the index, we'll say, is the place where an element is at, whereas the element is the data. College board goes by one. Yes, so that's a great point. So from now on, so Star Revamped, I hate to tell you this, but they're actually not going to tell you. So if I remember correctly, they're not going to say like, this list starts at one versus this list starts at 0. It's actually going to be told to you at the very beginning of the test in like a long list of instructions that tells you, by the way, we're starting all of our indexing at one. So what I would suggest you guys get in the habit of at this point is once now that you're kind of done with your create task where you may have started at 0, now we should always be thinking that we start lists at index 1. So kind of mindset shift a little bit. Does that make sense? I agree. Um, but yeah, so I think that idea of shifting our mindset now to starting at 1 is a good idea. So how can we use lists and strings to create data abstraction? So how can we kind of use this idea of strings, or I should say lists as well, to group things that are similar together? What do you guys think? This is more of an abstract question as well. So we can use a string to group multiple strings or variables into one large string to show a user. Sure. We can use a list to store similar data together for ease of access, right? Yeah, so we can assign a name to all the elements by using a list. That's absolutely right. So the idea is if we have a list, or yeah, let's say we have a list, right? Instead of having to say operate on the list, or let's say we have a list that's like this, right? We have a, so we have one, two, three, four, right? And we want to say multiply each number by two, right? Instead of having to go, okay, well, this is going to be, instead of storing them in separate integers, separate variables, say a equals one, B equals 2, C equals 3, and D equals 4, we can simply store them in one variable now, right? And just say list equals that. And so now by doing that, that decreases the complexity of our code, right? Because instead of having four boxes, all we have really now is one box that's storing a box kind of within it, right? So that's really where this data abstraction comes from, because now it's a lot easier to operate on a list than to say to operate on each individual variable by itself. So that's how we can use this kind of idea of a list, and the same thing with strings, right, to create more data abstraction and less complexity in our program. So that kind of answers this question. Why do we need to develop data abstractions? Well, it's because we want less complexity, right? All right, so now these I've kind of put in here. Um, these are essentially just what you're going to be provided with on the exam. So, for example, the exam reference sheet here is going to tell you here's a list, and if we want to say use this as a block, that's how we would see it in the block notation or the for whatever reason, AP likes to use this kind of block notation, so that's how you might see it. And then for an empty list, this is how it's going to look. As far as a copying a list from one to another variable, we can simply say, so say we had the list here. If we want to say list two and is a copy of our list, we can just say this in the exam. That's how we can notate that. So any questions with how we can notate stuff on the exam here with lists? Okay, cool. So in that case, let's go into some advice for the test. So the first is to be able to explain why data abstraction is necessary. So how your program creates data abstraction using a list. So essentially, the thing I just kind of told you about this whole like, well, instead of having to do this on multiple different variables, we can do it in one variable and use a loop to go through it. That's going to be something that you might want to memorize, right? Because they might ask you, how is this how does your I mean I can almost guarantee you they're going to ask you in your kind of free responses, how does your program manage complexity? And you can say, well, I manage complexity because I use a list that stores a bunch of stuff in one variable instead of separately, causing more chaos, not chaos, causing more complexity in my program, right? So it's actually causing less complexity because I'm using a list. Obviously, you may want to format that a little bit nicer, but I do recommend kind of memorizing that because you're going to be asked that for sure. Any questions with this idea here? Okay, so in that case, the next idea is pretty much just to be ready to answer some multiple choice questions about lists like this one. So let's take a look. A list employees contains the names and salaries of employees at a company. A manager wants to create high earners list, which should contain the names of employees earning $80,000 or more, sorted in descending order of salary. For example, if the employees contain, so this should be uh, employees, right, contains this, then the high earners list will contain here. So we see that Sierra makes 90,000, Priya makes 85,000, and Marco makes 80,000. So we need to take all of the ones that make more than 80,000 and sort them and extract their names and then sort them by salary. So here's our procedure and explanation of each procedures, right? So these are kind of pre-given procedures that we have that can operate on lists, right? So this is kind of the idea of the question is how can we operate on a list? So we need to figure out what the order is to call these procedures to get what we want. So we have these options here. but I think maybe it might be easier um, to actually just see if we can figure it out ourselves, right? So the first thing we might want to do is do what act? Well, I'll ask you guys. Out of these four procedures, which do you guys think we may want to end up doing first? We can filter by the salary, sort by descending salary. So in other words, so filter is going to get rid of anything that's less than 80,000. Sort by is going to sort the salaries, and then extract the names is going to extract the names, and filter top salaries is going to only take out the top n number of salaries. So what do you guys think would be maybe an order that could work for this? It's a bit tricky, right? So let's take a look at what we're given and what we want to get, right? So if uh, let's see, Star Revamp says filter by salary, then sort by salary and extract names. SV says filter by salary should be first. Well, it seems you guys are in agreement. So let's take a look at what answer choices would allow us to do that. We have A that filters by salary. B doesn't, C doesn't, and D doesn't. Well, look at that. We know the answer is A. That was easy, right? So let's take a look at why it's probably A. So, and I don't know for sure if it's A or not. We're figuring out this together tonight, so it's gonna be good. By salary, employees 80,000. So that's first going to get rid of everybody who is not 80,000, right? No worries. Welcome in. We're just kind of going through some questions on in this right now we're doing 3.2, but we're going to kind of go through the whole unit. So you're welcome in. Um, great. So in this case, we said filter by salary is going to be good to do first because we can kind of get rid of everybody who isn't uh, $80,000 or more. At that point, if we sort by the descending salary, then we'll get everybody who isn't. Sorry, then we'll get the correct order that we want. So Sierra, Priya, Marco, and then lastly, we want to extract the name. So if that's what that is, yep. So that would be A is our answer. No worries, no worries. You can always find the important notes in this document here. So if you scroll down to our lecture today in CSP, you'll find this sheet. Great. So let's go to 3.3, and we might need to take it up a little bit in terms of time because I don't think we're gonna be able to get through everything if we I keep going at this pace. So instead of kind of waiting for you guys to type, I may ask you half of them and I'll answer some of them. So what is an algorithm? I guess is a good question to start. So we can kind of say that an algorithm is you know kind of finite set of instructions that help us accomplish a specific task, right? Yeah, so a set of instructions to complete a task, right? As far as how algorithms can be expressed, well, we know we can code them, right? But what other ways can we express an algorithm in terms of instead of just coding, and maybe what they may want us to express them as? A recipe, sure. English, right? English is a great way to express, use our words, right? Yeah, so we could lots of ways. Pseudocode, diagrams, lots of different ways. Okay, what are the three steps to an algorithm? So every algorithm, what did you guys know these? Every any steps that we need to use in an algorithm? Okay, no worries. So um, we need a combination of sequencing, selection, and iteration. So these are the three that are going to let us derive or create an algorithm. And then we're going to be asked a lot of questions on these as well. The next is give an example of a mathematical expression, then state why it is so, or state why it's a math expression. So, what do you guys think? So, An expression is pretty simple, right? A plus B is whatever, right? Just like these are all types of expressions. And we can say they're expressions because they evaluate to a single value, right? So if they are evaluating to a single value, then that means that we can consider them a math expression. In what order or sequence do code statements execute in a program? So if I have, for example, three statements, statement A, top to bottom, right? Statement B and statement C, then we're going to go A, B, and then C, right? Now, if I have a procedure that I call as part of statement B, and that procedure is up here, it's going to go A, then B, and when it calls the procedure, it's actually going to go up to this procedure call, right? And come back down to C. And we'll see that later, but it's good to know. As far as for the test, we want to expect questions that ask conceptually about the steps of an algorithm, and then expect questions that give you an algorithm in English and ask you to trace an example of it. So that's what actually is going to be this one. And finally, we want to expect questions that use arithmetic operators while mainly testing other topics as well. So for example, that was what we had up here, right? Where was it? Right here. All right, so let us take a look at this practice question. So this is a little bit of a doozy, if I say so myself, or at least it is to read. So a bookstore holds an educational reading challenge each summer for middle school children. Consider the following algorithm, which simulates the event with 12 children participating. So I'll let you guys read these steps, and we basically want to figure out which of the following expressions or mathematical expressions indicate that the book thresholds that were generated in the simulation, which happens right here, were generated in the simulation, make enough money for the bookstore to break even. I should say make enough profit. So I'll let you guys think about it for a little bit. This one's a bit of a tougher one. So give it a shot. I'll zoom in, say there. And let me know what you think. You can put in spoiler. And this should be 12. Just initialize num children to 12. If you're just joining us, welcome in. We're doing a practice kind of multiple choice question here. It's a little bit of a tricky one. So I'm going to give a few minutes here to kind of see if we can figure it out. All right, let's see if we can work through this one together. So um, the question is, which of the following expressions indicate that the book thresholds that were generated in the simulation make enough profit for the bookstore to break even? So let's read the algorithm here. So the first things first is we initialize all these kind of integers, and then we initialize a list of integers books, or num books, I should say, 3, whose elements describe the thresholds needed to reach the next tier. Fill the list with 3 unique random integers between 1 and 15. Then sort the list in ascending order. So in other words, if you're the first tier, then you may have, say, 2 books to read. Then the next tier may have 5 books to read, and the last one may have 10, right? Is it B? I don't think so, but let's do it together and see. So I appreciate the guess though. So let's see. So next step is set children in tier to num children over 2 times tier. So here we said was one, right? So at this point, children in tier is going to be 12 over 2 times 1, right? So that's going to be, we'll say, 6. So we have children in tier to 6. The bookstore's profit for each tier is determined by the number of books they sell for children to make it to that tier. Each book makes, on average, $4 of profit. Therefore, increment profit by num books tier, so that's going to be num books of 1, which is some random number, right? Times 4 times children in the tier. So that's going to be times 6. So 24 times some random number. That's going to be the profit that they make. Next, each child in the tier is given a prize equal to $20 times the level of that tier. It's a nice prize, right? Therefore, increment prizes by children in tier times 20. Well, that's going to be, we know, 6 times, if we're in the first tier, that's 1, um, times 20, right? Is that right? Let's see. Yes, num children, 2 times 2. Yes, okay. So that's $120, right? Yep. So that's going to be $120 that the bookstore is going to need to give out to everybody in the first tier, right? Great. And then increment tier by 1 and repeat steps 3, 4, and 5 until tier equals 4. So let's see, what are we at? Tier 2 now, right? So if tier is 2, this is going to be num children is 4 divided by uh, num children is 12 divided by 4, which is 3, right? So we're going to have 3 children in the second tier, meaning that this is going to be incremented as well. The profit is going to be incremented, and the prize is also going to be incremented by, let's see, 3 times tier, which is 3 times 20, right? Is that right? 3 times, sorry, this is tiers 2. Except, yeah, absolutely. So the bookstore profit for each tier is determined by the number of books they sell for each children. So basically, this is calculating the profit, right? So each book makes on average $4 of profit, which means that the number of books that are in the tier that the bookstore is going to sell times the number of children in the tier, because each child in that tier needs to buy that number of books, times 4 for the amount of profit they make per book is going to get us the total number of profit they make for that tier, right? So if we're trying to track the whole profit, then they can increment the profit value by that number. Does that kind of make sense? The idea is essentially we're calculating the amount of profit that the bookstore is going to make for that tier. But in tier, do we put 3? Great question. So at this point, we're at tier 2, right? So this is the first tier, 6 and 120. We can't, I guess we should probably note that we can't actually calculate the amount of profit for any of the tiers, right? Because we don't know what number is going to be in this array. Um, Yeah, but in tier, do we put 3 as it initializes 3? Great question. So here we see it initializes 1, right? So then at that point, we'll have tiers 1 here, which means that we'll have 6 children in that tier. Tier is going to be 2 on the next tier once we incremented by 1, meaning that's going to be 3 for the number of children. And then in the last tier, we'll see that it's going to be 3 as it increments the third tier. And 3 times 2 is 6. So that 12 divided by 6 is 2. So we see that in the first tier, there's 6 children. In the second tier, there's 3. And in the third tier, there's 2. And so what we can do once we have this information is calculate the amount of that the prizes are going to be equal to, because we know this information, right? We know children in the first tier is 6 times the tier, which is 1, times 20 is 120, right? So then in the second tier, we see that there's 3 children in the tier times the tier number, which is 2, which is 6, times 20. So that's also 120, right? So that what that's meaning is that um, the bookstore is going to need $120 to pay out all the children in that tier. Kind of following? Great. Lovely. It's pretty complicated, right? But this is probably one of the harder questions that you could get. I kind of made this kind of really difficult for no reason. But that's okay. So let's take a look at then the last tier then, right? So if we have the third tier, we can calculate the prize money that they're going to need for that tier to be 3 times the tier number. Um, sorry, the children in the tier, which is 2 times the tier number, which is 3 times 20, which is again 120, which means that the total prize money that they're going to need for the whole competition is $360. So that's where we get these 360s from. Off topic, is college going to provide questions like yes. So I have seen questions where they kind of go through an algorithm step by step in English, and then they ask you a question about it specifically for expressions. By the way, my strategy without even looking at the procedure was that break even means they have to equal to or greater than would mean positive profit or something. And D is the only one that satisfies this requirement. That's a great, that's a good idea. So let's take a look at how would we get there, right? So if we have, because you're on the right track. So 120 plus 120 plus 120 is going to be $360, yeah? So we know that the prize is, if the prize is equal to 360, then we know that in order to break even, then you could say, so the prize is how much it's going to cost, right? So we need to know how much profit the bookstore is going to be making, yeah? So if we say that prizes is equal to 360, you're absolutely right to think that um, that's going to be kind of how much the bookstore is going to need in prize money, right? But if we're looking at the profit that the bookstore needs, then we actually know that the profit is going to need to be greater than the 360 in order to make a profit, right? Or to break even. So then we can say that you're pretty much right there. It's just there's a small trick at the end, right? Which is that this is calculating the cost of the uh, the the challenge. A is going to give us the amount of money they need to make. Does that kind of make sense? So I suppose if you want to be technical about it, right, break even, you could put an equal sign there to make it profit is equal to 360, and they'll break even. Kind of see how we're kind of doing this. It's a very kind of you're good. It's a you kind of got tricked a little bit, but the logic is sound. It's just that you need to add a little bit more to it, if that makes sense. Any questions with how we kind of did this one? So they could definitely ask you to trace an algorithm like this to see what you're going to end up at, and then to evaluate some expression based off of it. Yes, you just have to trace a lot. Okay, so let's go ahead and go into 3.4 then. So this is a little bit more straightforward, right? What is a string? A string is, just a collection of characters, yeah? It's a word, right? Yeah, so we can say it's an array of characters, or it's a collection of, sorry, it's a list of characters, right? I'm in Java mode. I do believe the test is going to be digital this year, yes. Okay, so um, what is a substring? That's a good question, right? Pretty much it's just a part of an existing string already, right? And then how can multiple strings be adjoined? Pretty simple, right? We just concatenate them. So string concatenation is a vocab word that is good to know as well. Yes, plus. Plus is exactly right. We can also use append, right? All right. So we want to be able to answer questions that use strings to test knowledge of other topics. Any questions with 3.4? Yes, yes. So concatenation is the string version of append, I should say. It does depend on the coding language. So in the AP CSP kind of pseudocode language that they use, you're going to want to use concatenate or concat, I think is the key word here, or the procedure name. if I'm remembering correctly. If not, somebody correct me, please. All right. Yes. Perfect. Great. So Boolean expression. So what does it mean for a value to be Boolean? True or false, right? It's either, yep, true or false. There's two options, right? It's either true or false, right? And then as far as the relational operators, first of all, what is a relational operator? Pretty simply put, it's just something that compares two things, right? It relates two things together. So that could either be A is equal to B, A is not equal to B, right? Yeah, you're listing all of them. I appreciate it. Yeah. So um, all we're saying is we're going to compare A to B using some operator to compare them, right? Weight is, so that is less than or equal to. Yes, it is relational. Yep. Not much. No worries. Welcome back. We're basically just talking about Boolean expressions at this point. Yep. Boolean is true or false. So here's a question for you. What does not and or do? So do you guys know what these are named? Conditionals. Yep, yep. Wait, why do we doing 3.5 booleans when we are supposed to be doing unit 4 lecture by John? Oh, sorry. I meant unit 3. Sorry. I just did a stats review that was unit 4, so I typed 4 by accident. Can I edit that? Let me see real quick. No, I can't. Okay, that's okay. It's we're doing unit 3 today. That's what scheduled. Um, I didn't, but I think somebody else may have. All right. So these are okay. I will note that. I may do that. So what do not and or do? Well, they simply let us compare two things, right? Condition and condition two. So if both of these things are true, then it'll evaluate to true. If neither or one of these things are false, then it'll evaluate to false, right? And it's the opposite for or, which means both of these or one of these can be true and it'll evaluate to true, right? So these are called logical operators. So there's relational operators and logical operators. So that's something we should know. As far as the test goes, we need to be prepared to answer questions specifically geared towards testing knowledge of Boolean expressions, especially logical operators. So let's practice with this question here. The diagram below uh, reverses operation. Yeah, so not is a reverses operation, or is true if one or both are true, and true if and only if both are true. That is a great summary. Thank you for posting that. Yes. Okay, so let's take a look at this question, which is like a logic gate, right? So we have a circuit composed of three logic gates labeled either and or or. There are also three modifiers labeled not. Each gate takes two inputs and produces a single output. The modifier takes in one input and produces one output. So if the if the final output produces false, which one, A, B, C, or D, is guaranteed to be false? So take a minute, answer in chat with a spoiler. Yeah, that would be crazy. I don't see them doing that though. That's just like cheap. If they shuffled the answer choices like this is B, that's like D, that'd be crazy. All right, so I'm seeing C's and D's. So let's take a look. So here's how we can approach these types of questions, right? If we start at the output and work backwards, we can figure out what it's going to be. So we know the final output is false, which means that if we not that or reverse it, then this AND gate needs to be evaluating to true, right? So if this is evaluating to true, then we know based off the and condition that Luke Mook, I'm gonna say is how to pronounce that name. That could be completely wrong. But we know based off of that that the and needs to evaluate if we want this to evaluate to true, then both sides of it also need to evaluate to true, right? So let's take a look. On the right side, we have another and, which tells us that we know that this needs to evaluate to true, right? Because this one said we said that both of these need to evaluate to true, right? So if this one needs to evaluate to true, then both of these then need to evaluate to true, right? So D we know has to be true, and C we know has to be the opposite of true, which is false. So we know that C is going to end up being what we need to be because C needs to be false in order for it to have switched to true, where this needs to be true, 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 false. Kind of confusing, huh? Any questions with how we did this? How not be? Great, let's do that. So we know that luck muck. Got it. Thank you. Nah, C sense or is flexible. Yes. So the reason why it could not be B is because we know that the left side of this needs to be true, right? Because then this needs to be true to be false, right? So, uh, sorry, when it says not at the end, does that mean that output is false and not true? So the output here is false, which means we need the reverse of this to be true, right? So this AND gate needs to evaluate to true because then at the very end it's getting flipped to false. Does that make sense? So the question was, why is it not B? And we know that this needs to evaluate to true, right? Well, we know that the OR gate can evaluate to true by having only one of these evaluate to true and the other one being false, right? So let's say that B evaluates to true because we say we want to prove that B doesn't have to be false. So let's say it's evaluating to true. Well, if not A, so if A evaluates to uh, false, right? Then not A is true, and true or true is true, right? So we have disproved that uh, B has to be false. Um, yes, I am not positive about the create task stuff, but I believe you do need comments. So I would add those if you have not done that. What up, D? No worries. So if this, we know that this side needs to evaluate to true, right? So this AND gate needs to evaluate to true, which means that both of these sides need to evaluate to true because that's how we would evaluate that and. So this D needs to be true, and this one then needs to be false, so that both of them, true and true, to get true. Questions? Any other questions with this one? I appreciate that. If you wanna leave feedback, you're always welcome to. I love positive feedback, but I also appreciate criticism as well if you have any kind of concerns or anything. Yeah, absolutely. I can say D one more time. So we know that this side needs to be true, right? Which means that uh, this is an AND gate, which means this also needs to have both of these be true. So D then needs to be true so that we get true, false, which switches to true. So both of these are true, evaluating this AND gate to true, evaluating this AND gate to true, evaluating this final output to false because of this not here. Very, very like true and false, not very confusing at some points. So yes, the answer is going to be C because C is the one that's guaranteed to be false. So D is guaranteed to be true. So if it was asking me the one that's guaranteed to be true, it'd be D. Okay, let's move on. Any other questions with this one? We may need to end up either skipping some questions or splitting this lecture up. Where can we view these questions to each unit? No worries. I didn't do a unit 1 or 2 review. I'm not sure if anybody else did, but you can find it here if they did. Also, like when we start tracing, is C or other letter true initially true? So when we started tracing, we essentially worked backwards, right, for this question. So what happened was uh, we started here saying false and then said, okay, well, this needs to be true then because of this not here, and worked backwards from there. So when we said, is C or other letter initially true, this D is the one that's going to have to be true, and then C is going to have to be false because it gets switched by this not here. Does that make sense? Perfect, perfect. Okay, let's go ahead and move on to conditionals then. So what does selection mean? So remember, selection is one of those three kind of big pillars of an algorithm, right? It was selection, sequencing, selection, iteration. So selection would be an if statement. That's exactly right. So what we can say is selection allows us to select which blocks of code we want to run, right? And we can use an if statement, which is what this is, right? To say if a condition is true, then we want to select this piece of code to run. So here is the exam reference. I think from now on, I think I might just skip this because again, we're kind of running short on time here. So let's go ahead and go on to some tips for the exam. So um, be prepared to answer questions that use conditionals and selection as a part of a question that tests other topics. So for example, let's take a look at this one. So this is from the mock AP Computer Science Principles exam. Um, so if you've not done that yet, and you would like to, then maybe look away for this question. But let's see. Let's take a look. This should be pretty quick. So the code fragment below is intended to display odd above 10 if the number positive if the positive number num is odd and greater than 10. So which of the following can be used to replace missing condition so that the code fragment will work as intended? So I'll give you guys a few minutes. Take a look at it, see if you can solve it. Put your answer in a spoiler if you want, and we'll come back. All right, so I'm seeing a bunch of A's, some D's. Sure, feel free. If you want to explain, go right ahead. I'm just gonna pull up the answer here so I know what the actual answer is. Um, 19. Okay. So I have some A's, some B's, some D's. All right, so like mod zero, mod equals zero is always even, but it says not. So that's odd. Yeah, right. So two equals zero? That's a good question, right? So sorry, mod two zero. Mod two equals zero. Yes. So we're looking for odd numbers, right? So that's even. So not makes it odd. Yeah, absolutely, right? So if num mod two equals zero, yeah, so fake kicker, you'll see that's you're actually the right one. But so let's see. So num mod two equals zero, right? So you're absolutely right to think that it's not A, but it's not A, but don't worry. It's your the reasoning for the first part is absolutely right. So num mod 2 is 0, but not makes it odd. That's absolutely right. But if we look at this next part and num is greater than or equal to 10, well, remember, we're only looking for numbers that are above 10, right? Is greater than 10, not necessarily greater than or equal to 10, right? So then your chat was right to think it's A. Uh, at first you may have been tricked to think, oh, well, this is true, right? This first part is true, and this is pretty true, but let's you didn't read all the other answers, right? So you have to make sure that we read all the answers. No worries, no worries. So your explanation for the first part was spot on. Um, so the question is A and D both right? Well, the question is specifically asking for greater than 10, right? So if we say the number is greater than or equal to 10, then that's actually wrong because the code fragment won't work as intended for the number 10, right? Because the number 10 will display odd above 10. It'll display true here, but it's actually supposed to not display true there. So then this odd and greater than 10, this is what we need to say is correct. Num mod 2 equals 1 considered odd. Yes. Yep. So anything that's num mod 2 equals 0, that's even, and anything num mod 2 equals 1 is odd. Pretty cool, right? It will display false because the first name is not correct. Uh, no worries, no worries. So, um, so A gives correct output. Let's see. So if we say if this is true, then we display this, and we're only supposed to display this message if the num is odd and greater than 10, right? But so let's consider what we would say, what if this would run or not for the number 10. Well, 10 mod 2 is 0, so that's true. Uh, so this is so 10, sorry. Ah, I see what you're saying. Yes, yes. Okay, yes, yes, yes. Thank you for correcting me. So that's actually a good catch because of so yeah, so what he's saying is this will not display because this works as intended, right? So that's a good catch. I think uh obviously I didn't consider that when I was ranking the question, but good catch. So if you said A, you're technically correct, but also make sure you understand why D is correct, if that makes sense. Cool. Cool. I'm gonna have to make a note of that to change. So yeah, yeah, you're all right. I didn't realize that it technically still worked because of the first part. So would College Board would just drop that question probably, to be honest. If there was something that like that happened, like a small typo or something, they'll probably just drop the question. But then they would adjust the curve so like as needed, you know. So I'm gonna make a note of that real quick. Look at this one to revise. Okay. So moving on, what is a nested conditional? So can somebody tell me what a nested conditional is? Pretty straightforward, right? It's just a conditional, which we said was if. Yeah, that's true. Actually, as a multi-select, that would be a great question. Um, so yeah, so I didn't so you're probably right. I didn't consider any of the odd stuff. So yeah, that's why I'm saying we'll drop the question, but I'd have to relook at that. So thank you for pointing that out. All right, so yeah, so yeah, well, that's what I was saying. Like I'm not sure because I didn't consider that 10 was not odd. So it probably should be 11, but that's okay. So we'll move on. What about the nested conditional? So um as far as a nested conditional, we know a conditional is the if statement, right? So if we say if something happens, and then we say if something happens beneath that, right? So a nested conditional, that's what that would be. So in other words, like for example, here we have an if here, else if here, else if again is in here. So these are nested within each other. So that's why they would be called a nested conditional. So we want to be prepared to answer questions that use nested conditionals. It's pretty common to have like one question like this. So let's take a look at this one. So what would be the displayed as a result of calling mystery 01. So, just as a real quick wrap up for this one, as long as we understand why this one is correct, we don't need to worry about the other answers because there's some errors in the other ones. So does that make sense to you guys? So that's what's going on with that. Yeah. So that there was an error in my part with the other ones. So, all right, let's take a look at this one then. Give you guys a few minutes. You guys can do the spoiler thing again. You guys know the drill. Yeah, so fake kicker, you're right. If anybody else wants to join in the answering fun, you're welcome to. Mm-hmm. Yep. So let's go over it. You can't divide by zero. That's absolutely right. So if v is less than zero, well, we say quitting anyways here, right? So we're not even gonna worry about that because that's not even one of the options. So if v divided by w is less than v, so that would be zero divided by one is less than zero, right? We would say then we display a, but that's not the case. So we'll go into the else statement. If w divided by v is less than w, so that's 1 divided by 0. Whoa, can't do that, right? So right away, we know that's going to be d. So any questions with this one? This is again just testing nested conditionals, right? All right. So iteration. So this is where we pick it up a little bit. So an iteration is basically just one step of something that you do multiple times, right? It's one iteration of something that keeps repeating. So iteration is that kind of third pillar of an algorithm. And we say that iteration statements kind of change the sequential flow, or I should say sequential flow of control by repeating a set of statements some amount of times until some kind of stopping condition is hit. So like this one, for example, or until we hit the number n. So what types of loop are there? Well, there's these types of loops, right? There's the repeat n times and repeat until. Some of you guys, if depending on your programming language, may know these as a for loop and a while loop, right? Uh, so as far as when does a loop stop, is it possible the loop may never stop? What do you guys think the answer is to that? It is possible, although it would be an error, right? So it would cause your code to crash because you'd have an infinite loop, right? While one is greater than zero. Absolutely, right? Yep, absolutely. So what happens when the conditioning repeat until loop is true initially? Well, if that's true, then we just don't go into the loop, right? We just skip it altogether. So we need to be able to answer questions about loops, but especially ones that iterate through an array. Note that two plus arrays being iterated through at the same time is something that's outside the course, the scope of this course. So really all you need to know is how you can use one loop to iterate through one, list is what this is called. I keep writing this in Java terms, but this is not Java. So through a list. Questions uh, that will also test your knowledge of infinite loops or loops that don't execute. That's going to be part of the like bug testing questions. And then finally, be able to explain how loops help develop data abstraction, which is kind of what we said before, right? So I would memorize that. So let's take a look at this one. This is again from the AP CSP mock exam. So if you've not done this one, you can avert your eyes, but yeah, let's take a look. So consider the two programs below, which are intended to display the length of a given list. Will the two programs display the same result? So here, obviously in this one, we have a loop, so that's why this is a practice question here. All right, so I'm seeing some C's. Very nice. So let's take a look. So, um, yeah, I think I agree with you guys. So let's take a look at why this is the case. So in program one, we're going to start at the number one And then for each item in the list, we're going to add one to that. So we'll have, for example, if the list is, say, 1, 2, 3, we'll have starting at 1 and then adding 2, 3, 4, right? So they actually add one more than this one does because if we just call length, we'll know that we'll see that this is a length 3, right? So since we start at 1 here and we add one for each number, the first program is actually always going to be displaying a number that's greater than the second number, right? So that's why that would be the case. Questions with this one? Pretty straightforward, probably, right? All right. 3.9. So we have some true. I decided to kind of switch it up kind of further in, add some more spicy, questions here. So true or false? Algorithms can be written in different ways and still accomplish the same tasks. What do you guys think? Is that true or false? No need to spoiler. This is we'll rapid fire these. True, absolutely. What about this one? Algorithms that appear similar can yield different side effects or results. Also true. All right, what about this one? Different algorithms can be developed or used to solve the same problem. Also true, right? It's like one of those brainwash tests where like they just tell you everything that you should know, and you're forced to say yes, 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 I know this. This is true. This is true. So yes, all these are true. So we should know that this is the case, right? Uh, okay, how can Boolean and conditional statements be rewritten um, to kind of be the same thing? Hey, I want to ask if you have a doc like this for previous units. I don't, unfortunately. I'm sorry. This is the first kind of year that I'm doing this, and this is the kind of the first unit that I'm doing. So I'll see if I can make this kind of stuff for later units as well. Okay, I'll take a look. So Boolean and conditional statements can be rewritten as each other, actually, right? So a conditional statement. So for example, if this is if this is true, can actually be rewritten as an and or an or statement. And so we can kind of rewrite these statements to be kind of equivalent to each other. Okay, how can an algorithm be created actually now is the good question, right? Um, well, we have a couple of options. The first is we can kind of have an original idea, um, and then and build an algorithm from the ground up. The second idea is that we can kind of use an algorithm that's already been pre-existing, right? And kind of just cheat, right? A little bit and kind of use functions, what do they call them here? Procedures to that have already been written to kind of build up a new thing, right? So that is very, very common in computer science. So when we get to libraries, that's essentially what libraries are. So as far as what we should expect for this on the test, we should be able to determine or be familiar with at least these algorithms. So determining the maximum or minimum value of two or more numbers, computing the sum or average of two or more numbers, identifying if an integer is or is not evenly divisible by another number. So that's mod, right? Determining a robot's path through a maze. So this is the fun part, right? So uh, we can do some of these questions as well here. So finally, also expect the questions ask you to compare two different algorithms, similar to shown here. All right, so let's take a look at this question. This is a fun one, and this is where students often are tripped up, I would say. So we want to select two answers. It's a multi-select here, and we have the question below uses a robot grid. I'm going to see if I can try and zoom in as much as I can here. Okay. The question below uses a robot in a grid of squares. The robot is represented as a triangle, which is initially in the bottom middle left square of the grid, facing toward the top of the grid. Which of the following code segments can be used to move the robot to the gray square? So we want to answer two kind of uh, answer choices here, right? So I'll leave it to you guys for a little bit to see if you can figure out at least one of them. I think one is a little bit more straightforward than the others, hopefully. Oh, and actually, this, I think I forgot to. Oh, no, no. Oh, yeah. Okay, we're good. How long is the lecture? Well, I scheduled it to 11, so I'm thinking it'll be probably closer to 11. We may end up not. I think this is 3.9. Yes, we may not be making it through the whole thing, but it'll go to 11. Sorry, 11 EST. So it's whatever that is in CST. The top of the hour, the top of the hour. So 45 minutes. You're good. You're good. So give this question a shot. I'll leave you guys like 5 minutes or so because it's gonna maybe take a while. Oh, Jake from State Farm. That's a great username. It's double bars on either side of the message. All right, so I'm seeing A, D, B, uh, B. So let's take a look. Let's take a look, see what happens. So, um, let's take a look. So I think D is a pretty common answer that we have. So let's start with D and see if that works. So we have A as well. All right, let's take a look. Let's see D. It's double bars at the top, at the beginning and end of your sentence. Okay. A, B. Okay. So we know it's not C at least. Okay, that sounds good. I think it's A. All right. So maybe let's start with A then, because there's a lot of people saying A. Thought of B as well. All right. So repeat 4 times. So we're gonna move forward. So that will place the robot here, and then move forward. So now, next we're gonna, oh, it's gonna repeat again, right? It's gonna repeat 4 times. So that was the first iteration. The second iteration is gonna go here. You guys see how this is gonna work out, right? Yeah, so I tricked you guys. I'm sorry. I hate to tell you guys, but it's not gonna be A, right? Because if we move forward once and then twice and then again the loop goes, and then again we go out of bounds, right? So it can't be A. And we know it's not C because nobody's saying C, so it's obviously B and D, but let's take a look at why B works. So repeat 3 times, move forward. So that's pretty simple. We're just gonna go 1, 2, 3, and end there, right? No, they don't. They go out of bounds. So if it goes out of bounds, then it's not right. As far as I'm aware, I could be completely wrong about that. And if you see somewhere that they stop at the boundary, then please tell me. But as far as I know, if they go out of bounds, gotcha. Yeah, so I think from what I've seen, it's mostly like you need a condition to say as like if you can move, then move, if that makes sense. Yes, please do that because if that's the case, then I would love to know that so I can edit this question. Okay, exactly. Yep. Um, so it's not A because it says to move four. It's 4 times 2 is 8 times, right? So it can't go all the way up to 8 times. So let's look at B. So B moves forwards 3 times, 1, 2, 3. So we're here. And then rotate right and move forward 1, rotate left and move forward 1. So we get to the gray square there, right? Okay, let's look at D then. So we want to rotate right initially. So that would be now facing this way. So if we repeat 3 times and repeat 2 times. So the first thing we're going to do is move forward, 1, 2, and rotate left. So now we're facing up. So we can repeat that whole thing again, right, from this repeat. Um, and we'll go. move forward twice, and then rotate left. So now we're facing this way. Use different. Can you explain analog? Can you clarify what you mean by that? Okay, so oh yes, like analog data. So that's going to be in a different unit. Yes. But I believe analog data is oh boy, it's been a while since I've done it. But if you take a look at the CED, if you just look up AP, CSP, CED, you can find analog data in there. Do you take AP, CSP, or UCs? I'm a CS minor in college. I did take CSP though as well. But I'll be honest, we don't ever talk about analog data in college. So it's something you need to learn and you'll never use again. But anyways, okay, so let's keep going with this. So we were here and then go left. So now we're facing here, and we'll go more forward twice, boom forward twice, and rotate left again, right? So now we're facing down. But as soon as we rotate start this next repeat, we're gonna rotate left. So if we're facing down, left is actually gonna be this way now, right? So we'll move forward once and rotate left again to face upwards, move forward and move forward one last time, and we're there. So it's a crazy, D is crazy, but it's right. Um, I don't like option D either, but what can you do? It's correct. How is cybersecurity field competitive? Whoever asked analog data is continuous. Yes, thank you. Continuous data is analog, whereas so like for example, a sound waves, right? Whereas digital is just ones and zeros, very discrete. Yeah. Thank you, Fake Kicker. All right, let's move on. So lists. What is the difference between a complete and partial traversal of a list? So let me ask you guys real quick, because we do have a lot more. We have like 9 more subtopics. So would you guys rather go through the multiple choice question practices or more of the more of these kind of explanations here and advice? MCQ. Okay, so let's just kind of skip right to the MCQs if that works for you guys. Yeah? Okay, mix of both. Okay, let's do like the advice then, I would say. Yeah, and we can kind of skip rest of them for now. Um, Here's what I'll do. If it's not possible to finish stuff, I'll end and I'll end and continue the recording. So if you guys want to say you can, but it'll be recorded, so we'll post the rest of it on YouTube. So, but we're gonna skip that and just go straight to the advice kind of stuff. So, as far as lists go, we want to be familiar with the following algorithms. So, determining a minimum or maximum value in a list. So, using a for loop, right, or some sort of loop. Can we do FRQs? Not today, unfortunately, but next time. And then we also want to be able to compute a sum or average. So we know we can add up all of them and then at the end divide by 2. So be able to determine the result of an algorithm that includes list traversals. And finally, we also want to evaluate expressions that use list indexing and list procedures. So let's take a look at this one. So the procedure below is intended to iterate through a list of cars called car list and replace every instance of a particular car, target car, with a different one called insert car. Which of the following procedure calls can be used to demonstrate that the procedure does not work as intended? So we have uh, procedure replace in car list, and all the parameters there, and we want to iterate through the list and see what's up. So I'll leave it to you guys for like a couple minutes here and see what you guys get. No worries, guys. If you guys need to go, you're welcome to view the lecture on YouTube as well. Yes, so we're recording all these lectures and then they'll be posted to YouTube shortly after they're like a day or two after they're done, hopefully. No problem. So yeah, have a good night. I should just be 5 hive. I'm honestly not sure. That's Outrage team stuff. All right, so let's go over this one. So, which of the following procedure calls can be used to demonstrate that the procedure does not work as intended? So let's kind of trace each of these and see if they work, right? So the first one is a list that has Honda, Ford, Toyota, and then the target car is Hyundai, which is not even in the list, and the replaced car is Toyota. Yeah, of course. I'm glad you liked it. Take care. Oh, and also, if you haven't already, feel free to fill out the lecture feedback form. I appreciate that. All right. Toyota is the insert car, right? So that's great. But if we repeat until the length of the list and we don't find this to be the case, then we're actually just not going to have to replace anything, right? So it actually works as intended. So A is not correct. All right, so now we have Honda, 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 Volkswagen, Ford. Well, it's the same exact thing, right? Volkswagen isn't in this list, so we don't even have to worry about it, right? Because we know there's nothing to replace. Ford, Nissan, Nissan, and then Nissan and Ford. Okay, well, if we look here, um, yeah, so it's going to be C. So uh, we see that Nissan needs to be replaced with Ford. But why does it not work? Well, if we insert at car list, index, insert, right? So if we insert the Ford, when we hit the Nissan, then the Ford is going to go here, right? But then the index doesn't change. So the index that we're on, index, the variable, is still 2. So we're just going to remove that Ford that we just placed. So really we're not actually replacing Nissan. We're putting in Ford and then taking it back out. So you see how that's the error here, right? Um, and then the last one, then you may be asking, well, why doesn't the last one work? Why isn't the index changing anything? Great question. So if the index were to change, we would see that index actually be changing in the function, right? So we'd have index equals index plus 1, right? If we did that, then it might actually work, right? Because we say Ford here, and then the index is now, instead of 2, it's 3. So we remove Honda. So that would work. But we don't have that there, right? So, and we'd actually need to go index -1 here as well. So anyways, yes, C is actually the only one that does something as well. So that's kind of also how you would know it would be the answer because D actually is replacing Audi with Audi, right? So it really doesn't do anything. So C, that's kind of a gimme if you get this one, right? If you know what to look for, then it's a gimme. If you don't, then if you have no idea what's going on, then that's a bit difficult. Then a bit difficult, right? So any questions with this one before we move on? Yeah, no problem. Why were A and B wrong again? No worries. So they're both wrong because they work. So remember, the question is asking for one that does not work. So A works because Hyundai isn't even in the list, right? So there's nothing to replace. So the expected outcome would be the same list. And because we're not replacing anything, this if statement doesn't get triggered. So it wouldn't actually um, replace anything, which is what we want. And it's the exact same thing. Volkswagen isn't in this list either. So I don't know if you got this right, if I got this right, but you would replace the Nissan with the Ford and then remove the Ford. Exactly. Yep. So maybe to clarify, you wouldn't actually be even replacing the Nissan because you're just inserting here, right? So you would be saying inserting the Ford and then just deleting exactly what you inserted. So um, you're not even necessarily even replacing the Nissan. It's not even that good. Does that make sense? Cool. Great. Wonderful. All right, let's move on then. Here's for your guys' reference what you'll be given on the test as a formula sheet. So binary search, I don't have any questions for this one, but the idea of binary search is basically what? You sort the data, right? So let's say we have a sorted piece of a sorted list, 1, 2, 3, 4, 5, 6. And in order to search for that data, instead of simply going through and saying, okay, is this one the 4? No. Is this one the 4? No. Is this one the 4? No. Is that the 4? Yes. Instead, we can start by splitting the data in half, right? So split the data in half here is 4 to the right or to the left of, say, 3? Well, we know it's to the right because the data is sorted, so we can eliminate then everything to the left of 3. And so now we only need to search here and say, okay, well, is it to the left or right of 5? It's actually to the left of 5, right? So we know right away it's 4. So why do you guys think we'd want to use a binary search over something like a linear search, which we described before? It's much faster, right? It's so much faster. And the reason why it's faster, and you guys don't necessarily need to know this, but it's maybe something good to know to kind of understand even more, is because you're looking through less numbers, right? So if you're going through linears, I did not stop sharing, I don't think. Um, if you're going through a yes, it's gonna be big O log n. Uh, yes. So the idea is if there are a ton of elements, absolutely, then it takes way less time because you can just do uh, kind of the comparison. Let me stop sharing and reshare for you, Nandini, and see if that works. All right. Um, Great. Perfect. So how many elements did it cut down to? Well, let's say we're looking for 5, right? So actually, let's say we're looking for let's see here. Um, 6, 7, 8, 9. You okay? So yes, it's going to be posted on YouTube. Don't worry. So if we are here 5, right, and let's say we're looking for 6, right? Everything to the left of 5 is going to be knocked out, right? So now we can look to the left of 7. And that's going to be to the left of 7, right? So we can knock out everything to the right of 7. So then we look to the left of 6, and it's indeed we found our 5. So that's 3 iterations, right? Instead of, say, 1 iteration, 2 iteration, 3 iteration, 4 iteration, 5 iteration, right? So it's going to be a lot less. And you don't necessarily need to know how much less it's going to be. But if in case you're curious, we can say it's always going to be the log amount of the maximum number. So in this case, there's 9 numbers here. So then there's going to be log of 9, which is 3. So it's going to be 3 iterations. Pretty cool, right? But like I said, you don't need to know that. That's out of the scope of the course, but you do need to know that's a lot faster. Okay, be able to determine the number of iterations required. Oh, I don't know if that's true or not. I'll have to double check the CED there. Um, but yeah, if you do need to know, then it's log. But if you don't, then yeah. Um, yeah, specifically implementations are out of the scope, so I'm gonna get rid of that right now. Just be able to explain the requirements necessary to complete binary search, and you'll likely see 1 or 2 questions about it. More general, high level. Why do we want to use binary search? That kind of thing. So calling procedures, very similar to how we've kind of done it already, but we can call a procedure. These are going to be the what? Parameters or arguments? Yes. Thank you, fake kicker. 1, list has to be sorted. 2, binary search saves times. Yep, parameters, because they're part of the function definition, right? As far as the arguments, when we call them, those are the arguments that we pass through. Perfect. Um, as far as what we need to be able to do is just determine the difference between the two and also determine the result of or effect of a procedure call, like we've been doing already. Here's some reference for you guys as well. As far as developing procedures, procedures like loops can be, provide abstraction because we can call procedures multiple times, right, for different scenarios. So if we generate a procedure that can apply to many different scenarios, then instead of having to do each of those scenarios separately, that would be very complex. We can just call that procedure that kind of generalizes that scenario. And we can call that, say, 5 times, for example, right? So that would be how we can provide abstraction. Okay, modularity is a big one, so let's talk about that. If you've not heard of that, that's okay. I didn't hear of it until I was putting this together, to be honest. So, but basically, modularity is just saying we can split up a computer program into separate subprograms, essentially, and those subprograms can be made up of procedures. So when we do that, we call that a modular program. So just another vocab to know. Yep. So like different functions, absolutely. So parallel computing, sequential computing is not something that's covered in this unit, but it's essentially using multiple processors to compute different answers or different subproblems in parallel versus doing each subproblem in sequence, if that makes sense. Yep, that's exactly right. So we want to be able to describe how we use procedural abstraction in your program. So in other words, how did you use your procedures to manage complexity? Libraries, very simple here. So I've never seen it asked on an exam, but who knows? Maybe you could get a question about a library. Basically, all library is a collection of parameters that have already been written that you can import into your program, and voila, you now have access to a whole host of new parameters. You do an API and documentation. Essentially, all those are telling you what parameters, sorry, what procedures. I don't know if I've been saying parameters, but I meant procedures. So, what procedures you have access to and what exactly they do. And so each kind of library should come with an API and documentation to tell you what that library can do. Any questions about what libraries are? So we can see how it simplifies the coding process because you don't have to write all those procedures. You can just import them. Pretty cool, right? Okay, random values. Yes, here we go. This will be another robot question. Fun time. So, what are the implications of using a random number generator in a program? So, in other words, what does it mean if we use a random number generator is going to happen with our output? Yes, so the computer doesn't always have an exactly random, right? But it can be pretty random, right? It can simulate randomness pretty effectively. But let me ask you this: Are if we have a parameter, sorry, oh my gosh, I keep saying parameter. I mean procedure. If we have a procedure that uses this kind of random uh, procedure within it, um, then the question is, are the outputs going to be the exact same each time? No, right? Because it uses randomness, right? So if we use a random number generator, then we're not always going to get the same output every time. That's pretty much all I'm asking with this question. Let me just double check on the CED that there's nothing else to tell you. Yeah, using random number generation in a program means each execution may produce a different result. And that's it. I think he's talking about me. I just did a stats lecture as well for 2 hours before this. So good times. Yeah, I got you. I got you. No worries. Um, yeah, but that's okay. That's okay. We're gonna get through it. So it's a fun time, It's a good time. I should be drinking water or something so I don't lose my voice, but yeah, no, of course. Yes, here we go. Hey, we gotta practice these, right? Um, so this question, the question below uses a robot and a grid of squares. Um, we don't. I got you. Yes, AP lectures are the greatest of them all. All right, so let's take a look for this code. So this is one of the harder robot questions for me at least. So uh, the code for mystery here is below. Assume that the parameter p has been assigned a positive integer value between 1 and 5, right? So we don't know what value is actually being assigned. Um, so which of the following shows a possible result of calling the procedure? And again, this is taken from the mock exam, so if you haven't taken that yet, avert your eyes. What does it say for repeat until, sorry, it says repeat until p is less than 0. So I'm seeing B, I'm seeing D. This is good. I'll give you guys a hint. Make sure two hints. So first is make sure that the robot is in the same orientation that you find. And the other hint is make sure that you don't end at zero, right? So it goes until P is less than zero, which means we have to consider the iteration zero as well. Yep. Yes. Zero mod two equals zero. I think you do get scratch paper. Do you have to re every time you increase? If you mean decrease from decrease the P, the answer is no. You'd start where you ended, if that makes sense. When D make it go back to the middle? Well, this is they're asking for where it could end. So if D would make it go back to the middle, then it's not D. If that's what if that's what you're wondering. Oh, Nate has C. All right, let's go over it. Uh, so yeah, Fake Kicker has C and Nate has C as well. So I think C is a good answer choice. But let's take a look at what really happens when we plug in different values, right? So um, if we plug in say an even number, so like two, right? Um, actually, let's start with an odd number. That would be easier. So, yeah, so there's kind of two options for this. There's the brute force method, which is kind of to plug in all numbers from one to five. And then there's the second method, which is to see what in general really it's doing in this loop, and then to kind of determine where you're going to end from there. So let's take a look uh, at an odd number. So if it's odd, then we're going to move forward one, rotate right. Uh, that's not going to evaluate, right? So we're going to stay here and be facing this way. But at zero, then, so we may think it's B, but it's not because we still have to do zero, right? So zero, move forward, rotate right, and then go into this if statement and go P mod 2 is zero. That's true. So we're going to move forward one, two, and rotate right. So now we're facing here. And so now we would move forward one and rotate right, right? And same thing. And you see, we're just going to be going around in a loop. If it started as odd, right? Um, but and so really it's going to be going around in a lopsided looping motion around the right side of the grid. It's really, yeah, it is interesting, right? If now we start, say, at an even number, say two, then we would move forward and rotate right. And then we would go into this if statement, right? So we would say move forward, rotate right, right? And then we go to odd, odd, sorry, rotate right. So we're here, right? Um, and so we go on to odd and say, okay, move forward and rotate right, and move forward, rotate right, and into the loop, into the if statement again. So you see how this goes into a looping motion up to the right side. So if we started at an even number, we would be going up to the upper right. If we started at an odd number, we'd be looping going down the lower right. So which ones of these could give us an answer? Well, this is in the left half of the grid, so we know that that's wrong. This could be right. This also could be right. This could also be right. So let's take a look at D. Well, we know if D is the case, um, that it would be tough to get that position, right? Because we'd be going up here. So I can kind of eliminate D. Let's say look at more specifically what would happen if we did two, right? So if we started here, move forward, right, move forward, rotate right. Then the if statement, move forward, rotate right. And then that would be now we're at P is one. So P, let's see, one is move forward, rotate right. And now zero is move forward, rotate right. And then the if statement, move forward, forward, rotate right. So we're in this square looking right, which is exactly where C is, right? So that would be yes. So good question. So let me for a quick actually erase the bold here. I accidentally bolded the right answer, so you guys would have seen it from a mile away. But yeah, so you're right. So that number randomly, that method randomly tried two. So there's that was kind of option one, which was start at one and then go to two and then go to three and go to four and go to five. The other option, which we kind of mentioned, was pointing out this kind of right hand loop, right? And saying, okay, well, let's just keep going and noting where we're ending uh, to infinity, if that makes sense. So like start at the highest number we can and just keep noting where we end each time. And so so in other words, don't worry about what number P is and just say, okay, well, if we start at an even number, this is what's going to happen. We're going to go up and then go down like this and then go like that, right? Or something like whatever it was. Move forward, right, uh, and forward here, rotate right. So this is one spot we could end facing this way. Then we could go end here facing this way. Then we could, you see what I'm doing is like I'm keeping it going until and noting where I could be ending, no matter what value P is, but knowing that we start with an even number. Do you see how that works? Okay, cool, perfect. Great. So let us keep it moving then. So a simulation. So what is a simulation? What's its purpose? Essentially they're just abstractions, of more complex objects or phenomena for a specific purpose. So in other words, can we simulate a real life scenario that we don't want to pay for or we don't want to gather all the resources for, right? So can we simulate it in a computer and see if that works, right? So why would we want to use a simulation? Like I just said, we don't have the resources, right? Simulations can be biased towards the real life or real world elements. So that would be something to note as well. Um, but simulations aren't ever going to exactly simulate the real world, even though they may often mimic it. They're not going to mimic it exactly. So it's always good to kind of uh, use as much as you can, but kind of take it with a grain of salt, if that makes sense. So they don't exactly make the rule as in simulations there are unlimited. Yes, exactly. Yep, that's exactly right. Yeah. Yes, exactly right. So the idea is we simplify the simulations down to what we're really focused on, if that makes sense. So we want to be prepared to explain why simulations, what they are and why they're used. So this is something to memorize as well. Like why they're used specifically is because there's not enough resources to do everything, right? Compare simulations with real world contexts, so on and so forth, right? So let's take a look at, I have two quick questions here. So number one is a hospital is planning a new emergency response system, and the administration wants to use a computer simulation to test different designs. For which of the following situations would a simulation not be well suited? So I'll let you guys think about this. We have comparing ambulance dispatch strategies to reduce average response times, comparing triage worker flows to improve patient throughput in the ER, Comparing alert systems to identify which ones notify doctors fastest, and comparing which patients should receive life-saving treatment when resources are limited. Yes, sorry. Comparing which, so B is saying comparing different, say, why don't we'll change it to this. Comparing different floor plan layouts to improve patient throughput in the ER. Does that make sense? We'll change it a little bit. Throughput is how fast people can get through the um, the floor, if that makes sense. How mobile the people are, or how how fast the nurses can move people throughout the where they need to get to, if that makes sense. So throughput is just like the amount that goes through. So when we're looking at questions, most of you are getting it right. So when we're looking at questions like this, where we're trying to determine where a simulation is not well suited, remember that simulations are generally going to be using random number generators to model real world scenarios, right? So um, we should be looking for things that have that can't be modeled using some random number generator, or in other words, can't be optimized, right? So a lot of the times when we're doing simulations, we're looking for optimization purposes, right? In other words, what is the fastest way you could do this, or what is the floor plan layout that that helps us move the most amount of people throughout the hospital, right? Um, so B is not the answer, because that's good. That's a good way to use it, right? We're optimizing the patient throughput. What may not be as good is comparing which patients should retrieve life-saving treatments. So, for example, this may be problematic because if we're trying to determine which patients to give life-saving treatment to, that has some ethical implications to it, right? We can't necessarily have computers be telling people, just randomly assigning patients to treatments, if that makes sense, especially if they're life-saving. So if the idea is there's the optimization here is more opinionated than the other ones. So for example, we're trying to reduce the response time here. So the lowest response time is pretty black and white. The patient throughput in the ER is pretty black and white, right? It's how fast can we get people through. Um, which ones notify doctors fastest? Again, black and white, right? what Comparing which treatments to save lives, determining whose life to save is not black and white, if you see what I'm saying. So that is why we'd want to choose D as the one that's not suitable for a simulation. Does that make sense? Questions? Um, yeah. mm, So the reason why we'd want to use a simulation in the first place is because of kind of the real life scenarios or the real life obstacles. But if the question asks us why something would not be suited, we don't. It's generally not going to be like, oh, because it's cheap to do. You see what I'm saying? It's because it's going to be more likely because it's unethical or because it just can't be modeled with statistics, if that makes sense. Cool. All right, let's take a look at this one then. An environmental agency is using computer simulations to model the impact of deforestation on a local ecosystem. Which are the following are reasons to use computer simulations in this context? Number one, computer simulations can help predict long-term changes in wildlife populations based on deforestation rates. Two, simulations can allow researchers to test various conservation strategies without affecting the actual environment. And three, simulations can ensure that deforestations only occur in economically beneficial areas. I'll restart my screen share. So I think maybe let's just talk through this one if that works. So the way we would approach this, yes, it is A. Good. So why are you guys saying A? So in other words, why is three not a valid reason? C makes no sense. Okay, yes, good. Uh, so economics doesn't have anything to do. In other words, um, yeah, there's no really reason to test it in economically beneficial areas, right? We're looking at the deforestation rates, right? So again, just some of them are more obvious than others, hopefully. Yeah. All right. 3.17. We're almost done actually, so we might get through it all. So, um, what is the difference between a problem and an instance of a problem? What do you guys think? So if I said, for example, sort this array, is that a problem or an instance of a problem? Instance. Why is it an instance? Oh, or is that or is that a question? I mean, you were right. Yes, it's one scenario of the overall problem, which is sorting a general array, right? So this is getting to more of the abstraction part as well, is that problems are more abstract, instances are more concrete. Cool? So, like we were kind of talking about before, let's classify these into decision or optimization problems. So remember, optimization problems are trying to optimize either the highest or lowest or whatever, right? Um, so number one, who has the highest rate in the class? Is that decision or optimization, do you think? Optimization, right? Because we're not saying uh, it's not black or white, right? We have to choose the best grade. Even if the grade is black and white, choosing it is not. Is there anybody with a 100% in the class? Decision or optimization? Decision. Yeah, you guys got this. Am I closer to Philadelphia or Paris? Decision, right? Because black or white, right? And then this is pretty obvious, right? I should have used the word optimal. uh, so anyways, optimization, yeah. Optimalization, yes. Um, so, um, what is efficiency in terms of an algorithm? So how can what does efficiency mean, basically? How much something takes. How much time something takes. Yes, great. So, it's basically just the amount of computational resources, right? That's used by an algorithm. How efficient? Oh, yeah, no, we can't say how efficient. Yeah. No. So it's just how much, resources it takes, right? And then how is it expressed typically? And don't say big O because that's not in the scope of the course. But I'll say why we have this graph here later. But okay, so I'll give you guys the answer. So we can express the yes in terms of time, right? And more specifically in terms of the input size, right? So if, for example, our input size uh, is large, then we may get more. It may be less efficient. That makes sense. So we want to express it in terms of the input size. Now, again, formal analysis, so big O, and formal reasoning using mathematical formulas are outside the scope of this course. But knowing what how efficient algorithms are or what algorithmic efficiency is important. So, what is the meaning of the following graph? So, okay, so let's take a look at basically uh, this kind of. So, okay, we're gonna go over a little bit of big O, but it's not gonna really be what it means. So, basically, these are lines or graphs of what the input sizes may be, right? So, for example, if the input size is just a constant, for example, just the number one, then we see that the line isn't even visible, right? It's even is way below this like red line, right? Or for example, if we have log n number of inputs, then it's actually going to be very small comparatively, right? Um, so as you guys can see then, as we kind of grow our sizes, it's gonna the in the long run, these like for example, factorial or exponential are gonna go really fast, right? Compared to something like a polynomial or linear arithmetic is what this is called, which is just n times log n, or like just a regular linear, right? So you see that these two are really growing like really fast, right? So what that means is at even like small input sizes, like three or five or 10, right? Even at 10, uh, when our input size is relatively small, functions that take this amount of time are going to take so much resources that they're not going to be worth it. Do you see how that kind of makes sense? Where if our functions take like like the time that our function takes can be expressed by an n factorial amount uh compared to our input size, then it's going to be really slow. Yes, it's exactly that. It's how much effort the computer is taking, right? So compared to the input size. So for example, if our input size is n, or for example, if our input size is 10, then if our function is taking 10 factorial amount of operations or amount of, effort, then that's going to be way slower, right? It's going to grow at a way slower rate, or in other words, it's going to grow the function itself is going to grow fast, but the computer is going to be slow, right? At very high uh, number of inputs. Does that kind of make sense? It's kind of weird, but um, it kind of is important, especially when you get into like bigger and better, things. But um, yeah, so these ones, no worries. So n is the number of input sizes that you have. So again, don't worry about this notational stuff. N is the elements. Yes, exactly. So N is what you're giving into your, say, function or to your program, right? So again, don't worry about the notational stuff, but worry about how something that takes uh, like constant, linear, square, cube, any polynomial efficiency is going to be a lot more reasonable than either of these two, exponential or factorial. Uh, at the bottom where it's close to the X. Yeah, so it's more operations as you go up, which means as you go up, the more operations you do, the slower it gets. The slower your computer is, basically. So what we say is that these two, the or in other words, um, algorithms that run with a polynomial efficiency or slower, or in other words, uh, so linear, constant, any of these ones, right? So anything but these two, these are all reasonable. So that's a key vocab word. The word is reasonable time. These two, though, are unreasonable. They run so slowly that we consider them an unreasonable amount of time. So we don't ever want to write functions or algorithms or procedures, I should say, because we're in CSP, that take this amount of time. That makes sense? So the idea is uh, that yeah, algorithms with polynomial efficiency or slower are said to run in reasonable amount of time. Algorithms with exponential or factorial efficiencies are examples of runtimes or of algorithms that run in unreasonable amount of time. Okay, questions with this graph. All right. So, what is a heuristic? Any questions or any answers to what a heuristic is? It's getting late. No worries, no worries. It's really not that it's really not that big a deal. This is not going to be a huge part of the exam. Like I promise you, it's not. They may ask one question about what like a heuristic, um, but but it's good to kind of know it just in case. So, uh, yeah, no worries. So a heuristic, you guys can always watch like a YouTube video or something as well. It's kind of like trial and error. Basically, if, for example, we have a function, or sorry, I keep saying function. If we have a procedure that we want to do, but it runs in an unreasonable amount of time, then we can do a simpler function that may not give us the exactly correct answer or the exact optimal answer, but it should give us a solution that is good enough. You know what I mean? So, uh, if we can find some sort of procedure that runs efficiently compared to an inefficient, exactly correct answer, but this more efficient procedure gives us a um, somewhat correct or a good enough answer, good enough is the key word, then we would use it. So that's what a heuristic is. Okay, so good enough. So we want to be familiar with a heuristic is how many they apply to everyday life. This is the big one. So you're going to be definitely asked like a question or two probably about a heuristic and identify scenarios where heuristics may be appropriate. Also explain the difference between algorithms that run in reasonable time and those that don't. And just memorize. No worries, no worries. I'll go over it real quickly. So it's not a problem. So the idea is with algorithmic complexity or algorithmic efficiency that algorithms that run in what we call uh, exponential and factorial time are unreasonable. So we don't want to use them. But algorithms that run in anything less than that, so polynomial, so squared, cubed, or constant or linear or anything, those are reasonable. So if we have a function that runs in one of these two runtimes that we don't want to use, but we can use a different function that runs in one of these runtimes that gives us a good enough answer, then we'll use that one, and it's called a heuristic. That makes sense? Kind of. If not, that's fine. We'll do some practice right here. Okay, so let's do this one. So there's two more questions here, and that's it, I think. So, oh no, there's one more, but even, that's not even anything. So, um, let's take a look at this question. So, a software company is developing an app to use, a software company is developing an app to help users plan road trips across the country. Which of the following components of the app would most likely benefit from the use of a heuristic, which remember is a good enough answer? A, converting distances from miles to kilometers. B, calculating fuel efficiency based on user entered data. C, finding the shortest scenic route that includes multiple landmarks. Or D, formatting the trip summary into a printable PDF. All right, so I'm seeing some Bs. If anybody else wants to chime in before we go over it. B. All right, cool. So let's go over it. So, um, I think we may some of us may be going with the herd, but that's okay. So let's first of all look at A. Let's kind of look at A and then D first. So converting distances from miles to kilometers. This is obviously not right because this is a simple formula, right? So if we have some sort of, I don't know, it's like whatever. Well, I don't even know what it is, but it's like it's a constant that you just multiply, right? So if this is the case, then this is going to be a really quick function. Yeah, it's going to run really quickly because it's just a formula that you can just plug in, right? So we don't need a heuristic for this because it runs in a reasonable time. What about D? So D says formatting the trip summary into a printable PDF. So again, this is pretty simple. It's just kind of the formatting is an algorithm, right? It doesn't really there's no really optimization to it. There's no questions or anything, right? It's just a pretty simple algorithm. So it's going to be running in a reasonable amount of time. Let's look at B. So calculating the fuel efficiency based on user entered data. So if the data that we enter um, gives us some, some list of places we want to go, whatever, right? We can calculating the fuel efficiency depends on the trip, right? But once we have the trip, then it's pretty simple. It is C. You'll see. Um, so you're good. So once we have the trip, you'll see. Yeah. Once we have the trip though, it's pretty easy to calculate. Oh, well, if it's 60 miles, right, then you'll need this amount of fuel. So this is actually a pretty simple formula once we have the trip, right? So finding the shortest scenic route that includes multiple landmarks. So if I say I want to go from Philadelphia to, uh, you know, Jacksonville, Florida, right? Then there's a lot of different paths you can take to get from A to B, right? And especially if you say, okay, I also want to go to Charlotte and I also want to stop in um, Washington, D.C., see the White House, that kind of thing. Like, um, there's a lot of different paths. So this is going to be a very difficult or a very or an algorithm that may run in an unreasonable amount of time, right? So heuristic is trying to be like not simple, but horribly unreasonable. Yeah. So a heuristic is just saying if this we know is going to take a very long amount of time, then what we can do is find, instead of considering every single possible route from Philadelphia to Jacksonville, let's just consider like the four major highways, right? And then from there, which one stops in the most landmarks? So that's a good enough answer, and that runs in a much better time. Yeah, so in this scenario, it's probably just going to be the most complex answer because it takes a long time. So that's why we'd want to use a heuristic. Cool. All right. So let's go to this one then. So see, we can see if we can apply what we just learned. So Jordan is a game developer working on an open world adventure game where the non-playable characters, NPCs, must find paths around obstacles and reach their goals efficiently. To ensure smooth gameplay without lag, Jordan chooses to implement a heuristic-based algorithm. Which of the following best describes the role of heuristic in this context? A. The heuristic is a set of random movements NPCs make to simulate realistic wandering behavior. B. A heuristic is a mathematical formula that checks every possible path to guarantee the shortest one. C. A heuristic is a strategy that guides the pathfinding algorithms. I see you guys are all getting an answer here. Let's see. Uh, yeah, you're all saying C. So yes, the heuristic is a strategy that guides pathfinding algorithms to estimate the best route quickly without checking all possible paths. Uh, and D then heuristic is a debugging tool to use. It's not right. Yeah, so yeah, it's pretty straightforward once you kind of pick up on it. This type of question is a lot easier, I would say, than this type of question, right? And that's it, I think. Let's see. First of all, any questions with heuristics? We can do like one more question if you guys want, um, from like the mock exam. Okay. Mock exam, what's it called? Practice test, I think. What did I call it? One second. I'm gonna pull it up. Here it is. Okay. So this is the practice test that's linked to the top at the bottom of the document. Heuristic. All right. Rick has been tasked with developing a scheduling system for a conference where multiple talks and sessions need to be arranged without conflicts. Given the complexity of this and number of sections, Rick decides to use a heuristic approach. Which of the following best describes the role of heuristic in this context? Again, this is this is like a very like straightforward, type of problem they could give you. very like um, template based, very similar to the Jordan and NPCs problem. So yes, it's going to be B, a method that uses an educated guess or practical strategy to generate a quickly generate a good enough schedule, even if it's not the optimal one. No worries. So what are you confused about, Nate? Yes. So so an optimal schedule is one, remember that because this conference has multiple talks and sessions that need to be arranged without conflicts, the optimal schedule may have zero conflicts, right? Whereas the non-optimal one may have two conflicts that they can then resolve, right? Yeah, so that's a good enough schedule. No. Yeah, yeah, yeah. I got you. All right, let's do one more if we can find one. Heuristic. Yeah, okay, that's the only one. So, which of these programs is most likely to benefit from the use of a heuristic? A program that converts between Celsius and Fahrenheit, a program that optimizes the layout of items in a warehouse to minimize retrieval time, a program that compresses video file to reduce size, or a program that checks the spelling and grammar in a text document. Great. So the question is, which one of these is going to be the most complicated? So, yeah. So the idea is uh, we heuristics are trying to optimize something, right? So a Google Doc or a spelling and grammar thing. So we're mainly between D and B, right? So B is the right answer. Uh, But the reason D is not correct is because, or maybe I should say is less correct, right? Again, these questions are we're answering for the best, or the best answer that we can, not necessarily the only correct answer, right? So you could use a heuristic to check the spelling and grammar one, but it's not likely to benefit from a heuristic as much as B would. So the reason is because spelling and grammar is pretty simple. You can kind of store all the words and then see if any of them have typos, right? Whereas B, the layout of an items, there's lots of different kind of layouts that you could have, right? Whereas, spelling and grammar, I mean, you either spell it right or you don't, right? Whereas the layout, you optimize. Can I ask you questions if I'm confused about something? Yes. Yes, it's permutation. Exactly. Nate, I couldn't have put it better. That's exactly right. It's permutation, factorial type stuff. Yep. That's okay. This is a good stage to be at where you think you get it, but you could get a little bit tripped up. Just keep practicing with it and you'll be good. No worries. All right, so as far as algorithmic efficiency, was this the same one as what we did? No, no, this should be undecidable problems. Okay, so what's the difference between a decidable and an undecidable problem in the computer science? The idea, um, is, sorry, real quick. For some reason, messed up my CD. Okay, so a decidable problem is a decision problem. So we know the decidable, so we remember what decision problems are, yes or no, right? So this decidable problem is a decision problem for which an algorithm can be written to produce the correct output for all inputs. So correct for all inputs. Whereas an undecidable problem may have some uh, correct answers, but they can't provide a correct answer for all inputs. So that's the difference. Can't for undecidable. Yep. Yeah. So just be able to explain the existence of undecidable problems, and you will not be asked to determine if a problem is decidable or not. So that's a plus. Heuristics. So not necessarily. Um, I like this thought process though. This is good. This is good, like thinking. So the reason why we'd make a heuristic is if a if an algorithm that we're trying to find an answer to is not how do I want to say this? So it's not necessarily that the problem is undecidable. But it's more that the problem, even if it may be decidable, but it just takes really long to get the answer, if that makes sense. But if a problem is undecidable, then you can use a heuristic to find it, if that makes sense. So it's like not all triangles, not all squares are triangles. Oh my gosh, not all, it's late. Not all squares are rectangles. Not all rectangles are squares, but all squares are rectangles. You know what I mean? So it's like that kind of thing. So undecidable can be correct for some inputs, but not all. Yes, that's exactly right. Yep. It takes forever, but that gets the correct answer for heuristics. Yeah, that's why you'd want to use a heuristic is because it takes too long. Cool. All right. Not all people who are male. Okay. I'm not gonna read that one for the recording. Yeah, okay. So thank you guys so much for joining us. If you guys want to do this small activity, I'll leave it in the chat, but we don't have time to do it. There's five quick questions. You guys can do that as in 7 minutes, and the answers should be programmed in. So yeah, of course, here's some more resources for you guys if you want. Like I mentioned before, if you guys could fill out this, I would super appreciate it. Yeah, of course, no worries. I appreciate it. Yeah, of course, of course. Um, not a problem, guys. If you yeah, like I said, if you guys want to leave any suggestions or just want to, I don't know, tell me how amazing I'm doing, that's fine too. But I appreciate that. So, all right, I can send you guys the this document as well. So you guys can scroll down to these more resources as well. So, all right, thank you guys so much. Any other questions I can answer real quick? How long is small activity? It's 10 minutes or so, 5 to 7 minutes to complete these questions and then going over it. I let me check my schedule here. So I have a music theory review here, and then what do you guys know when your test is by any chance? May 15th. Oh, yes. Okay, I'll have time. If yours is on the 15th, I'll definitely have time between here. So I will have to schedule it. I'll probably schedule it this weekend or so. But it'll probably be somewhere in here. So yeah, absolutely. Cool. All right. If there's no other questions, you guys can always feel free to reach out over Discord. My DMs are open, so if you have any other questions, feel free to reach out. Cool. All right. Good night, y'all. Take care. I have the most people in here because I'm the only person doing anything. Yeah. Good night, guys. See ya. Yes. I'll send this link to the outreach team who should be posting on on YouTube here soon, probably next couple days, hopefully.